Welcome to ECE 501B, Advanced Linear Systems Theory. Hopefully we will have everyone here that is planning to be here in the classroom, and we'll be able to notice that by the attendance sheets that are going around. And if you need to sign into the class, sign attachment 1. If you're already in the class, sign attachment number 2. If you're watching this online or remotely, send me an email. You won't be able to touch the sign-in sheet, either one of those. Please make sure that you have access to D2L. If you have a U of A account, you should have access to that, and the website is hopefully available for you, and you will be able to then find these lectures that I will PDF and post online, and also the video capture. I will probably make that available to you also. Just as an announcement, and this is how I will start. I'll give you some announcements and then I'll give you some goals. But the first thing is that you need a passport to get into the class. And that's available on the D2L website. You should be able to find that on the content page. Click over to content, and under Unit 0 Preliminaries, you will find the passport assignment. That's due on the last day of August, which I believe is a Saturday. There is no game. You have the game the day before, Friday the 30th, so you shouldn't have to worry. And I think I've made this available at 11:59, so I haven't completely destroyed your entire evening. You can still have from midnight on, so Sunday you'll be able to do whatever you need to do, which is probably study for this class. Okay. Our goals for today, we've already accomplished quite a few of those. Attendance sheets, these are being recorded, these lectures. The passport assignment, if you get on the D2L website, this is what you will see. The first thing is, what's your name? If it's John Smith and you go by Billy, then your nickname category needs to be Billy. Hopefully we don't have any John Smiths in here. And I'm not trying to offend anybody. Give me the email address that you use. An up-to-date photograph. Maybe as a part of this class we'll learn how to filter those kindergarten pictures to age progress you to the present day, but I'm not going to use that right now. I need your present day photo so that I can see you as you are now. What's some fact that might set you apart from your friends? Maybe you're double jointed with a thumb. I don't know. Maybe you can juggle. Maybe you ride a unicycle. I've had most of these as a part of the unique feature of you. Maybe you just really like to study. That's fine. But give me something that I can focus on besides Billy and your picture. Usually it's helpful if I have some fact in addition to your nickname and your photo to connect with you. Then, just as an exercise, go to this North Carolina State University website, determine what your learning styles are, just as a point of reference. Tell me a little bit about how that might impact your participation in this class. Then there's a past, present, and future question to address or deal with. And finally, there's this contract. You can type your name. You don't have to sign it and scan it. If you don't want to, you can simply type your name in there. That you will deposit in the Dropbox on D2L, that submitted passport. And hopefully by the end of December after the class, I will know your name. We'll see. I'm going to have a few students, not just this class this semester, but that's okay. We'll try to make sure we get to know each other a little bit better. Another goal today is to talk a little bit about the course by means of the syllabus, and this also is on the D2L website. My name, which I guess I didn't ever say, what did I? I'm Hal Tharp. I will be your instructor, I believe, unless I kick myself out for the semester, but you can find me during office hours, which I have those 3 days a week, Tuesday and Thursday mornings at 11 to noon, and Wednesdays basically right before class. Class is Monday and Wednesday from 4 to 5:15, and they're in ECE 102, and what we will be using for all of the exchange of information is the course website, which is found on D2L. There's some general information about the course, which you've probably already seen. There are a couple of required textbooks. One of those you will be able to assess or find or obtain the PDF form on the D2L website, so you won't have to buy anything. The author has been kind enough to allow us to use that material. It's a PDF. Linear Algebra Done Right is the one that you will want to acquire, and there were some copies still in the bookstore a week ago or sometime last week. I don't know how we're doing now. There's an optional book on how to read and do proofs that will maybe be helpful for you. I might also on the D2L website provide some links to other resources that are textbook in nature. So be alert to that. They're not listed in the syllabus, but we'll see how that goes. We will have 2 1 hour or single period examinations in addition to the final exam. I don't know how many homeworks we will have, but in terms of the point breakdown, that's right here. And probably already what you're concentrating on is when you're going to get out of this class. Next Monday we will not meet. Labor Day, you do not need to show up. The building will probably be locked, or it should be locked. You should be studying, but that's now the first time we won't be meeting. In terms of breakdown of points and grading, we will have 2 exams during the course of the semester, and those are the tentative dates, early October and early November. Then we will have our final exam on Monday, the 16th of December. So buy your airplane tickets accordingly, not before that date. That sometimes presents a problem. But also note the time. It's a little later than the class. It's 6 to 8 p.m. So have maybe your dinner before the final so that you're not just rolling out of bed at 5 p.m. and showing up for the final. You may want to have some nourishment before the final exam. And we will have project, which we will discuss subsequent to today, and homework. Those 2 will each be worth 10% of your grade. The bottom half of page 2 of the syllabus really just gives you the index of the first book, which I will refer to as Axler, but that's Linear Algebra Done Right. The second book is Signal Theory by Franks, and we will get into that, and hopefully we will start to understand the connection between those 2 textbooks. Ideally, if I give this early enough, maybe you can sort of read those in parallel and you can see the analogous systems or the concepts that are analogous to both domains or to both textbooks. That's the idea. Are there questions on the nuts and bolts or the organization of the class? If not, let's move into the class material, which is item 2 and item, well, I don't know what item it is. Anyway, the next to the bottom and the last item on the goal list, where we've covered all of our goals. So if you're into accomplishing goals, you can check things off. The first one I would like to try to motivate or provide an overview of the class, and then we will get into chapter 1 of Axler. I guess I did do a little scanning before class of the front covers. If you're looking for the first textbook, that's what it looks like. It's a yellow text with some vector diagrams on the front cover, which is illustrating some of this linear algebra that we will be playing with. And the other one is what you will be doing most of the semester, is thinking. That's the how to read and do proofs. Whoops, I forgot to give you a picture of the one that I will be providing to you. I don't really even have that, and I think the one that I found on the internet was so small you might not be able to see it anyway if I posted it on the screen. But you'll be able to get the second text, required text, which is Signal Theory by L.E. Franks from the D2L website. Let's now see if we can motivate a little bit this course and provide a context with which to be thinking about what we're doing when we're working through this material. And first of all, we are playing in this domain of linear system theory. The generic way of thinking of this is consistent with a lot of block diagrams that you will see in the curriculum. If you go through a standard electrical and computer engineering curriculum, you may have some system, and that system is then connecting input signals with output signals. And what we are going to do in this particular class is view this connection of input and output as a mapping or as an operation. How do you connect signals in the input domain or space with signals in this output domain or space? Now, this particular picture or diagram or schematic is made up of two things, signals and systems. And that signal and system structure is common to a lot of different areas of application. Maybe I should say is very common. For example, if we just think about putting in a column what the system might consist of, you might be interested in playing with that block diagram in a controls perspective. Then the system block that can be expanded upon might contain actually multiple blocks, but in general, that might then consist of the plant dynamics or the system itself, which could be just an electrical circuit, it might be a mechanical system, it might be another type of system, it might be an electromechanical system, it might be a thermodynamic system, a chemical system. You may want to change the way the input and the output are appearing or behaving in that particular system by the design of the controller. And knowing how to manipulate and play with those pieces is what you're going to learn in this class. Another possible area is signal processing, where a very basic, or maybe I should say a very all-encompassing way of thinking of the system is to just view that as some filter. Maybe you have a noisy signal and you want to filter it. It might be that simple, but it may be something a little more complicated. Maybe you are now trying to manipulate that signal to perform something or infer some new information from the output signal. So in that block, you now might have a filter. Or maybe you're looking at something from a communications perspective. Now you might have a lot of different blocks, and in particular I'm thinking of the early parts of the signal theory textbook by L.E. Franks. He has a large block diagram that is all absorbed in my big block of system, meaning you might have a transducer that measures this physical signal. Then you might try to encode that information. You may have to transmit that information over a large distance, and it may be inefficient to just scream it, so you might have to modulate that on some high frequency waveform. Then it's going to go through this channel, we'll just say the transmission channel, and then you have the backside where you now might have a demodulator, a decoder, and then another transducer potentially to give you back the information that you want. And this you might just say is sort of pre-processing. This is now maybe the post-processing. And you have the transmission channel. And all of these pieces now are combined or collected into that one block that I was calling a system. But now all of these pieces now are interrelated, and it might be up to you to figure out what kind of transducers you need to use, how you need to encode and decode the information, how are you going to modulate your waveform, etc., in order to obtain the most effective communication channel or communication system that you're dealing with or using. You might also have this in many other settings, and here I'll be less specific since this is getting outside maybe my main domain of interest, but you might have an optical system where you might have light as the input and maybe light at the output, and you have this optical hardware in the system block. And you might want to design some of that optical hardware to manipulate the signal to achieve the output signal that you're looking for or trying to generate. Now the nice thing about, and this applications areas could just continue on, but what we are going to do is actually generalize this in terms of these topics. We can generalize and fold what I will say a large number of these application areas into a common mathematical framework. And that's what we want to do in this course, is abstract away some of the details and just concentrate on the mathematics. And our abstract math environment will be what you can call this area of linear vector spaces. That's where we will be playing. And we can go a couple of different ways in very broad strokes. We could talk about linear algebra if we restrict our attention to dealing with finite dimensional objects. And that's where the first book is living. That's Axler. Or we could go into what's referred to as functional analysis. In that case, we have now gone into this infinite dimensional domain, or let's say continuous waveforms, and now that's Frank's. That's the other book that we will be working with or working from. And what I've tried, or what hopefully we will start to see, is that both of these domains actually share many features. And what we are going to do is we will try to take advantage of what we maybe learn or better understand in the finite dimensional domain and translate that information into the infinite dimensional domain and allow us to learn a more broad and general understanding of those two topics or that material. We will try to take advantage of what we learn from one domain to understand the other domain. And in terms of learning theory, that's very powerful. You want to actually relate what you're learning new with something that you already feel comfortable with. And maybe initially some of this linear algebra stuff will be a little bit new, the way that we're presenting it, but you'll start to get very comfortable with it. Then we transfer that knowledge or that comfort into the infinite dimensional domain, and now you'll be able to understand that a little bit more thoroughly or a little bit better. Now, what we also are trying to do with this course is we're also going to try to develop our mathematical maturity. And we're going to do that by not discarding, by not shying away from proofs. Meaning this first book that you're going to see is full of proofs, theorems and proofs, and we need to figure out how to think that way so that we do raise our level of mathematical maturity, and that's going to be very essential when you're pursuing your advanced degree. Being able to pull a paper out of a journal and read it and start to understand it a little bit more effectively than, oh, what in the world is this guy talking about? I'm not quite sure what's going on here. He's got a theorem. Well, we'll start to hopefully decode some of that so that now you get a little bit more comfortable with the way that theorems are written, and that gets back to that third text, how to read and do proofs. What does it really mean? Oh, he's sort of written this in a very terse way, but I can now fill in the gaps. I know how to fill this or complete this in my own head, and now it makes more sense. What we will do is we will try to make these connections and what I will say, we will use some interesting / fun papers to connect the theory with reality. Reality seems to be used in a lot of things in the media, right? Reality TV. Well, now we're going to have reality ECE 501B, right? We may not be on camera, may not be filmed, but we're going to try to connect what we're doing in class or what might happen in the real world with the theory that we work with in class. For example, we will look at a paper on, principal component analysis. And that may not make any sense to you, but right now you'll at least be able to maybe recognize that description or that phrase. And this paper really is talking about what if you have some data and you want to try to understand it, and maybe you really don't know what's in that data. This could be big data, for example. Now, how do we extract meaning from data? And what we will see in that paper, and this may not mean anything to you now, but hopefully it will start to make sense as we move throughout the semester. But now this principal component analysis is dealing with symmetric matrices. And what do symmetric matrices allow us to do? Now that provides us with special features associated with eigenvalues and eigenvectors. And in particular, we might be able to look at the SVD or perform the SVD computationally, SVD, singular value decomposition, on this data to try to learn where are the main directions or where's the interesting data aligned, or how is this data maybe organized. And we may just see it as an abstract collection of points. But with this paper, hopefully we'll learn a little bit more about principal component analysis and how that relates to the theory that we'll be talking about, which are symmetric matrices, eigenvalues, eigenvectors, singular value decomposition. What semester are we in? Fall, right? And what happens in the fall? It also starts with an F. Football. All right, maybe you're not into football. Oh, and this is American football. Maybe you're really not into American football. But maybe you might see this floating around, BCS. You need to leave that C in there. Sorry. So now we have the bowl. And I need to be able to spell. I'm getting so excited now I can't. I'm going too fast. Bowl Championship Series. And maybe even Arizona might become competitive in their football, maybe. But this is now a way of ranking these Division I football teams and deciding who gets to play who at the end of the season. Well, there's actually a paper that we can look at that will provide us with another strategy for ranking football teams just based on their win-loss record. And maybe what we can do is we can just sort of follow that along through the Pac-12 season and see how it's moving, how the teams are organizing themselves based on their win-loss record against each other. We could maybe reduce that from the 120-some teams that I don't remember the numbers. But this is now dealing with positive matrices. So now you start reading, oh, positive matrices. Oh, that's related to football. So you can relate these ideas to different concepts in reality. That's the point. All right, maybe you're not into football. Maybe you're more into the computer. And when you talk computer now, you're always talking Google, right? Well, not always, but sometimes that might surface. And Google has become popular because of its ability to sort or rank web pages. And you probably, when you think of Google, you probably don't think about eigenvectors. But that's how they sort, or that's how they find the important web pages. And somebody has put that information together into a paper that's called, whoops, I don't need to overemphasize that, do I? That B stands for billion. Maybe I should. The $25 billion eigenvector. I think they get that number from what the company was worth when it first went public. So now these guys are sitting around figuring out, how do we put this information together? Oh, we can do eigenvalues and eigenvectors, and if we find this alignment, now we can figure out how to rank these pages. And that's really just an eigenvector problem. So we'll talk a little bit about that when you'll be able to better understand Google PageRank once we get more comfortable with eigenvectors and, let's say, other matrix concepts. So that's supposed to motivate you. This class has a lot of connection with reality. And you're going, oh, linear algebra, row reduction, eigenvalues. That's pretty exciting stuff, actually, if you can figure out how to apply it. And the singular value decomposition, that's a strong concept to understand. That might now allow you to find the 4 fundamental subspaces. What in the world is that? And you'll be more comfortable with the range space, the null space, and their orthogonal complements. There's their 4. And what that means. What does it mean to be in the range of something? Let's then start walking through the material. And this will give you something to do tonight, because I know that you want to begin studying if you haven't already. So I apologize if you've been looking for the last month on the D2L website trying to figure out what you need to do. But hopefully you knew what the textbook was and you've already read it. But let's start with Chapter 1. And Chapter 1 is dealing with vector spaces. But before we get into vector spaces, let's just try to lay down a little background information and the strategy that is used by the author or by Axler. In this text, we're not going to get too general, TOO. We will do 2 different, what mathematically is called a field. But that's really just a set, or sets, if we have 2 of those, sets that we are going to pull numbers from, or objects from, and in our case it's going to be numbers. So these fields are sets from which we will draw numbers. There's one notation that we will use, this R with a second vertical line, and that's going to be the real numbers. Or we might be drawing our numbers from this set of the complex numbers. Which really is just a collection of 2 real numbers that are orthogonal. And they're orthogonalized, let's say, by this square root of minus 1, where A and B are such that A and B belong to or are elements of the real numbers. And that's what this little epsilon looking character is defined to be. This is an element of, is how you can read that. A and B are an element of the real numbers. Now the textbook simplifies the notation sometimes because a lot of times we can actually prove these simultaneously for both the real numbers for our field and the complex numbers for our field, or many times we will be able to prove results for both fields simultaneously. And when that's possible, then we just go ahead and abstract that R and C out, and we replace it in the textbook with a new sort of double vertical, which is this F. So F means that we either can use a field of real numbers or a field of complex numbers. That's what we're meaning. So now we have this potential to use two different sets of numbers. We can either be playing in this sandbox that has real numbers, or we can go over here and play in this other sandbox that has complex numbers. And that will be where we are drawing our numbers from. And once we have those real or complex numbers, now we can start building things with those. And the first thing that we will build is a list. And in Axler, that list is really just going to be put into an ordered set in like a vector. That's how we will be viewing those. So this list is an ordered group of, let's say, n objects. And in Axler, those objects are going to be numbers. But you could have a field, if you define it properly, of some other more generic objects. But we will probably be boiling things down into more specifics where our objects are either real numbers or complex numbers. And this list then might be written as subscripted variables, x sub 1, x sub 2, on up to x sub n. There are n objects that are in a list, and the order matters in that list, but all of these x's, x sub 1, x sub 2, up to x sub n, are elements either of R or C. They're either real numbers or complex numbers. Meaning x sub 1 could be 1 plus j2. And x sub 2 could be minus 7. X sub 3 could be 4 plus j10. And that's now this collection of complex numbers. And if n was 3, we would be done. That would be our list of 3 elements from the set of complex numbers. That's our field. And we could then specialize this to various cases. If little n is 2, then we have this ordered pair. The order again is important. We can't just reverse the order and keep that item the same. It would be different. If n is equal to 3, then we have an ordered triple, and we could just keep going. For the generic n, we now have an n tuple of terms or objects in our list. Sometimes we might get tired of writing all of those different components in our list, and if it's possible, we might just abbreviate that as a single variable, maybe this variable x, to represent that n vector. So when possible, we will use a single variable to represent all n components in that list. So we might just refer to it as x, where x is now meaning x sub 1, x sub 2, all the way to x sub n. And I kept trying to indicate that that order of these terms or objects in this list are important. This is not a set. This is a list. And there's a distinction between a set and a list. Let's just make that explicit by this note. A list, ooh, that's pretty. A list is not a set. Order, and we could even have these elements repeated. Repetition, order and repetition are actually important or do matter in a list. For example, here's maybe what you could think of if you just wanted to see the distinction. A set might be containing 2, 4, and 4, but that's really just equivalent to a set that contains the number 2 and 4, or a set that contains 4 and 2. However, if you were dealing with a list, 2, 4, 4 is not the same as 4, 2, 4, which is not the same as 2, 4. That's the distinction that we are making. This is a 3-vector, or this is an ordered pair, and those are not the same. They're not equivalent. Whereas a set might contain just 2 objects, 2 and 4, and this one also contains 2 distinct objects, 2 and 4, and it really doesn't matter how you've ordered those in the set. We also have components when we have a list or a coordinate. I may use those interchangeably, but we now can refer to a coordinate as one of those elements in a list. For example, if we had x consisting of this n tuple, where we now have a vector, well, a list of objects, x sub 1, x sub 2, up through x sub n, x sub 1 is what we will refer to as the first coordinate. Obviously then, x sub 2 is the second coordinate, And we could just go on all the way down to x sub n is the, let's call it the nth coordinate. And once we have these lists, now we want to be able to perform some operations on those lists. And with a vector space, we really just have two operations to worry about. Vector addition, and vector, you need to be more abstract with how you think of it. Vector is just an element of a vector space. It may not be this long, skinny, tall vector or long, narrow vector that we're used to thinking of when we say a vector. It could be something different. It might be a matrix. It might be a polynomial. Because it belongs to the vector space, it's now a vector. Hopefully that will start to make a little more sense as we move forward. But let's now talk about how we are going to agree to these two different operations. If we have a list, then it's pretty clear. For example, if we wanted to talk about addition, when we're dealing with this list, then it's just element-wise or component-wise addition. Our list addition is element-wise addition of the coordinates. Meaning, if Z is the sum or the addition of a list X and a list Y, then that is simply going to be the first component of X plus the first component of Y, the second component of the two lists, etc. So we're doing that coordinate-wise or element-wise in these first coordinate, second coordinate, nth coordinates of these lists. And that then we could refer to as Z1, Z2, all the way up to Z sub n. That's one of our operations that we want to define when we're talking about vector spaces, and that's addition. It seems pretty basic, but we can generalize it. But for lists, it's pretty straightforward. It's sort of what we're thinking it should be in terms of addition. Then another operation that we want to have at our disposal is scalar multiplication. I don't know why I said A. Let me just say multiplication of one of these lists that we'll pull out from our vector space. So now we have this list. We're going to take that list, a multiplication of a list by a single number. For example, A might be coming from one of those fields, either the real numbers or the complex numbers. That's a single value from that field. We now multiply that list by a single number, and we're not multiplying a list by a list. So it's multiplication of a list by a single number and not multiplication by a list. That's pretty ugly, but hopefully you know what I'm trying to say. And this is now defined as element-wise multiplication. By this scalar. Meaning if we wanted A times our list X, now A is coming from either this field of real numbers or field of complex numbers, but that's just one number, and we use that same number and scale all of the different components of that list in X. So that we now have A times X sub 1, A times X sub 2, A times X sub n. And now we have three things at our disposal to create a vector space. We have a set of objects, these lists, and we have addition and scalar multiplication. And those three objects are going to allow us to create this new thing called a vector space. So here is now our Chapter 1 concept vector space, and you can find eventually its definition on page 9 of Axler. And what you may want to sort of keep in the back of your mind is this main idea, and we've simply introduced that information in just the previous discussion. We wanted three objects, and those three objects consist of a set that's either real numbers or complex numbers, with two operations. Vector addition and scalar multiplication. And here, you might just try to keep track of the fact that this vector is not necessarily the typical thing you think of when you start thinking of a vector. The vector is simply an element or elements of the set, where that's this set of lists made up of real numbers or complex numbers. And that's, let me say, an abstract usage of this term vector. So don't get locked in when somebody says a vector. It doesn't necessarily mean this row vector or column vector. It might be a polynomial. It might be a matrix. That's now a vector because it's coming from this set of items that we are using to define this vector space. All right, so now let's define the vector space. A vector space is any set, which the book likes to use V, any set V of lists that has the following properties. If we pull something from that set, let's say that we pull two things from that set and we add those up, their addition needs to be contained in that set. Meaning, another way of saying that is this addition operation is a closed operation, meaning the addition of these two lists or these two items from the lists are contained in this linear vector or this vector space. That's when x and y started in that vector space. So if you have something from V and another element from V, you add those up with this addition that we've defined, and the result ends up in V, then that's what we need as one of the properties for us to have a vector space. It needs to be closed under addition. This vector space also needs to be closed under scalar multiplication. Meaning if we pull something from that list, x, this vector, and we pull an element from our field, either of real numbers or complex numbers from Axler, then if x started in the vector space and a is coming from that field, and also all of the components of the vector x are in F, then if we scale that vector, and you can just think of either elongating or contracting if you did have a vector. Now think of this vector in this two-dimensional plane, possibly. Now you can define that point or the tip of the vector by an ordered pair. If you scale that by, let's say, a real number, you have either collapsed it, shrunk it, or elongated along that same direction. But that scaled vector needs to be in that same space or in the vector space. It needs to be closed under scalar multiplication. Now that we have that, we want to have the following basically 6 properties hold in order for us to have a vector space. We need closed under addition and closed under scalar multiplication, but now we need to have the following properties. Commutativity, which means it really doesn't matter the order with which we add those lists. X plus y is the same as y plus x. It better not matter in this vector space when x and y both begin in the vector space. It also shouldn't matter how we collect or associate these sums together. The end result will be the same. So we might add x plus y and then add that result to z. That better be the same as x plus y plus z. And we also have associativity with respect to multiplication by a scalar. We could either multiply a and b and get a new scalar and then use that to scale the list, or we could scale the list with b and then rescale it with a, and that better be the same. In these two cases, we're pulling these vectors or lists from the vector space, and all of the pieces, a, b, those were scalars from our field, as are each of the elements in these lists. The components of x, or the coordinates of x, the coordinates of y, and the coordinates of z are all living in that field of real numbers or complex numbers. We have commutativity, we have associativity, we have an object that we will call the additive identity, which really means to say that we have a 0 in our vector space. If we add that 0 to any element, we get the element back. So 0 and x need to belong to that vector space. We also need to have a multiplicative identity, meaning if we scale that list by the multiplicative identity, which we will just represent by 1, then, whoops, what happened? Oh, I probably erased it by emphasizing that 1. That 1 times x is just going to give us x back, where x is any element in the vector space. We also need to have an additive inverse. Which says that every x in our vector space, V, there exists another element in V that when added to x gives us the 0 element. So that's our additive inverse. For every x, no matter which x we pull out of that vector space, there exists a y in that vector space such that x plus y gives us the 0 element, or the 0 vector. And here, hopefully it's clear from context whether 0 represents a list where every component is 0, or whether it represents the scalar 0. So we could take the scalar 0 and scale a vector, and what will we end up with? We will end up with a 0 vector. That's after we've put all these pieces together. The other thing that we need, how many do we have so far? We have 1, commutativity. We have 2, associativity. We have the additive inverse, the additive identity, which is just the 0 element. We have the multiplicative identity, which is really just the 1. We're not really scaling anything. We have the additive inverse. That means we can find any 2 elements in that vector space when added together gives us 0. And we finally have the distributive property, which says that, so there's property 6, we could add 2 lists, x and y, and scale by a, and that would be equivalent to scaling x with a and scaling y with a, and then adding those 2 scaled values or scaled lists. So x and y are both starting in V. And another distributive property is if we have 2 scalars, a and b, and we then add those, then scale x, that's equivalent to, again, the right-hand side that we had, well, not quite what we had above. It's now a times x plus b times x. Again, a and b and all the components of our lists are in this field, either the real numbers or the complex numbers. Let's just sort of try to think about some possible vector spaces, and we'll try to make it a little bit more than just what we're used to thinking, although we'll give those obvious examples. Now, what are some examples of vector spaces? V might represent r to the n, which this is really just an n-dimensional vector that has for its elements real numbers. So r to the n is a vector space. And this simply symbolizes the fact that each of these n vectors in this list are real numbers. And that's what you're used to thinking of maybe when you think of a vector. We could also have a vector space, V, that has elements that are complex, c to the n. This is an n-dimensional vector with elements in C. Now, those are sort of the ones you would have expected. Let's now look at some that maybe you hadn't thought of as vector spaces. You could have a matrix that has M Michigan rows and Nevada columns, where each of those, maybe we write it as C raised to the M by N. What does that mean? Well, these are now M by N matrices, where each element in that matrix is coming or is consisting of a complex number. Now, this is where you can really start to maybe thinking more abstractly. Now you have a matrix, but now you could call a matrix a vector because it's an element from a vector space. That's why I said don't get too hung up on how we're using this term vector. Now a vector could be a matrix. Can I really confuse you? This some element, this matrix, let's say Michigan is 3 and Nevada is 4. So this is now a matrix that's 3 rows by 4 columns. We're saying that now, by these earlier properties, can be viewed as a vector space, where we now have element-wise addition and we have scalar multiplication in the general sense of how you would define those addition and scalar multiplication operations. Meaning, let me just sort of in brackets try to describe what I was just saying. We can call these matrices vectors. The reason we can do that is since the matrices, let's say it's a 3 by 4 complex matrix, these matrices are elements or objects, let's say, of the vector space. So we now have this collection of 3x4 matrices, and if I just pull one out, I can say, oh, that's a vector. If I pull another one out, that's another vector. And now I can add these vectors. And I can perform scalar multiplication on those vectors, where those vectors are really these objects that are matrices with complex elements. But that's how you can abstract out this concept of a vector space. So we don't just have to live with long, skinny vectors that we're thinking of. We can have vector spaces created from different entities or different objects, and one of those could be matrices. What's another potential for a vector space? We might have a vector space, let's say p to the n, or p sub n, where this is now an nth order polynomial. Meaning we might have p of z, where we have a sub 0 plus a sub 1z plus a sub 2z squared plus dot 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 plus a sub n z to the n. And the a's are coming to us from this field. The z's are also belonging to this field of real numbers or complex numbers. And now that we have, let's say, an n-dimensional polynomial, now that collection forms a vector space. And you would have a different element for each of the different z's that might live in those particular spaces. One more. We can actually even generalize this to an infinite dimensional list, which is we never terminate that list, meaning now maybe we have z, that is z1, z2, z3, and we just keep going. And that would be then this element of c sub infinite, or c to the infinite subscript, where each of these z sub i's are complex numbers. And we would just then say, okay, we have a z. That's a vector. That's a list. And order and repetition matter. And that could just go on forever. Now somebody might give you a y from that same set. Well, you can add those up. You just add them up component y's or coordinate y's. You could scale those by a scalar. And this now satisfies those properties that we listed, those 6 properties of a vector space. So we don't just have to live with these fairly basic vectors that you might have thought about when you were talking or when you had your first experience with maybe linear algebra. Now we can generalize that to where now are these vector spaces, might be a set of real vectors, it might be a set of complex vectors, or it might be matrices, or it might be polynomials, or it might be infinitely long lists that form these vectors. All of those are potential vector spaces, and now what we want to get more comfortable with is how can we play with and what kind of properties do these vector spaces possess and have. Questions? Your clock is hard to see because it's on the black of the screen, but I will say that we're finished with today's lecture, and we'll pick up at this point. Start looking over Chapter 1 of Axler, and we'll see you on Wednesday.